Right, in the previous lecture we talked about the coloring vertices so that the adjacent vertices get distinct colors. In this lecture we will have a different coloring. Instead of coloring vertices, we're going to color edges. Okay, so that's why I wrote the edge coloring. So again, let's define precisely. So let us be a set of colors. And then on edge coloring of G, maybe it's convenient to look at the definition for vertices because everything will be almost the same. Right, that was vertex coloring. Now the edge coloring of graph G is simply a function C from set of edges to the set of colors such that CE is not equal to CF whenever E and F are adjacent. In other words, EF share an end. Right. So if set of colors is 1 up to K, then C is called sometimes it's proper K as coloring. Okay. And then we also say K as colorable. And what else? The chromatic, so the chromatic index or sometimes it's called the edge chromatic number. Usually denoted by chi prime G is the minimum K such that G is K edge colorable. Okay, now another, by the same way we can think of it as a partition of the edge set, right? If we color G with the K colors, what does that mean? Each color class has a set of edges where no two edges are adjacent. So that is what? That is a matching. Assuming there's no loops, right? If G is loopless. If you have a loop, then I mean, it's we can say matching, but matching plus loops. Okay, matching plus loops, their pair is not adjacent or something like that. All right. So then, what does that mean? That means chromatic index is at most K for a loopless graph. G if and only if the set of edges can be partitioned into K matchings. Okay? Because each color, if you have a partition into K matchings, then for first matching you put one color, for the second matching you put second color, for third matching you put third color, etc. And that will give you edge coloring. Right? So this is if and only if statement. So the edge coloring is really like the matching problem in many ways. And as we did for vertex coloring, we can compare the edge chromatic number with the maximum degree. But here, what's striking is that this is true. If you have a degree delta, maximum degree delta, then the chromatic index is at least delta. Yeah, let's ignore loops, because when you measure the degree, loops are counted as 2, right? So that's annoying, right? So this is so delta is 2, and chromatic index is 1, right? So it's convenient to ignore the loops. That's because we define degree to be each loops are counted as 2 edges. All right. So this is strange, because remember, for vertex coloring, we knew that chromatic number is at most delta plus 1, but this gap could be huge. For instance, for planar graph, there is a graph whose maximum degree is arbitrarily big, but chromatic number is small, right? So for instance, you can have a tree. Yeah, I didn't even need the planar graph, just to have a tree. Chromatic number is 2, right? And the maximum degree could be arbitrarily big. So in the vertex coloring, the maximum degree and the chromatic number could be very far. But for edge coloring, that's not the case, because if you have a maximum degree delta, then you have a vertex of degree delta, and then all these edges are of different color. So any graph with the maximum degree delta should have a delta distinct colors, so therefore edge chromatic number is at least delta. And moreover, it's easy to see that edge chromatic number is at most, let's say, if I have an edge, how many edges is it? Is it adjacent? Well, I have edges like this, so this is delta minus 1, that's a delta minus 1, right? So this edge is incident with at most 2 delta minus 2 plus, right? So we can write like 2 delta minus 1. Why? Because I take a line graph of G. Oh yeah, so by the way, this is equal, right? Edge chromatic number is equal to the chromatic number of the line graph. There's no need for any condition, right? Right. Remember, line graphs are the graphs on edge sets. So the two edges are adjacent if two edges are adjacent in the line graphs, even if the corresponding edges share an end. So the maximum degree of the line graph is at most maximum degree of the graph G times 2 minus 1. So therefore, minus 2. Thus we obtain this. So this is strange in a sense. So this means that if maximum degree delta is big, then edge chromatic number is big, and if edge chromatic number is big, maximum degree is big. So they can be almost within some constant factor, so they're not very different. And in certain cases, we can actually determine edge chromatic number precisely. So when can you determine it? And that's a theorem of Koenig. So here's another theorem of Koenig, 1916. If G is bipartite, then edge chromatic number is equal to the maximum degree. Why? Why is this the case? It's actually not quite difficult. We just remind this theorem, so that if G is a K-regular bipartite, then G has a perfect matching. Right? So if you have a bipartite graph with every vertex having same degree, then you have a perfect matching, as long as K is at least 1. So what's the plan? For the proof of this Koenig theorem, we're gonna find the matching, perfect matching, and remove it, and the maximum degree is decreased by 1, and then repeat this inductions. To do that, actually I'm gonna reduce it to a problem on regular bipartite graphs. So how do we reduce that? So let A be a bipartition of G, and let delta be the delta of G, and we're going to do induction on right. I mean, should I do the induction on delta? Yeah, let's do induction on delta. So what we claim is, if you have a bipartite graph with the maximum degree at most delta, then edge chromatic number is at most delta. That's what we're going to prove. And it's trivial if delta is 0. And now what we're going to do is the following trick. If you have a place that you can add an edge, then I will do that. If I can do it without increasing the maximum degree. Right? So we may assume A or B has no vertices of degree. Okay, let's say A has no vertices of degree delta. No, degree less than delta. Okay, let's say this way. What do I mean? Otherwise, if I have a vertex of degree less than delta here in A, and vertex of degree less than delta in B, then what we can do, we add an edge. And adding an edge doesn't make a problem easier. It only makes problem harder. Edge chromatic number will increase. Edge chromatic number can only increase, it cannot decrease. So if we prove the same theorem for the case where if you prove the theorem for this bigger graph, then you prove theorem for this smaller graph automatically. So whenever I see two vertices of degree less than delta, it's okay to add an edge between them, and problem is only getting harder. So that means at least one side. Yeah, so one side, every vertex is degree delta. So let's say, so we may assume all vertices in A have degree delta, right? So everybody here has degree delta. Otherwise swap AB. Right? Otherwise you change A and B, and I think it's the same by symmetry. Now, how is it possible that B has a vertex of degree less than delta? Well, that's because so this means that the number of edges is equal to delta times size of A, and it's less than equal to delta times size of B. No, not less than equal to, because every vertex in B has degree at most delta. So this means size of A is less than equal to size of B. Now, what we're gonna do is we will add. Alright, so okay, what's gonna be the good way to do that? Induction on okay, let me add a parameter. So I'm gonna alright, so with the same delta, I will be happier if the difference between A and B is smaller. Okay, so I added it into the parameter, so why not? Right, so if A is strictly less than B, then we add an isolated vertex to A, which doesn't change any problem because it has nothing to do with edge coloring. We didn't introduce new edge. Then this in the new graph, let's say A prime. Okay, so let A prime B with the bipartition of this new graph. Let's say G prime, and since delta of G prime plus A prime minus B is strictly less than delta of G plus A minus B. So the edge chromatic number of G prime is at most delta. So that implies the edge chromatic number of G is at most delta. Every year I show you. Every year I show a different proof. So this year, this is the proof. All right. So that means whenever these two parts have different size, I can add one isolated vertex and win by induction. So we may assume size of A is equal to size of B. But then by this inequality, what inequality? Yes, by this double counting inequality, what we end up is every vertex in B has degree delta. So G has a perfect match. And then when you delete it, the maximum degree of G minus M is equal to delta G delta minus 1, right? So G minus M is delta minus 1 edge colorable. So when you delete a perfect matching, you can partition the remaining edges into delta minus 1 matchings, right? So now use one new color for this matching M, so the edge chromatic number of G minus M is at most delta. So that's the proof. Okay? Yeah, so whenever graph is bipartite, determining edge chromatic number is easy. Because I only need to look at the maximum degree. This is very nice, right? Bipartite graphs, chromatic number is easy because it's 2 or 1. Edge chromatic number is equal to maximum degree, so everything becomes easy. Now, in general, what can we say about general graphs? Right? Is this inequality tight? Is this tight? And that's not tight for many cases. So here's a theorem due to Wijing in 1964, saying that if G is a simple graph, then edge chromatic number is at most delta plus 1. and at least delta. And we knew this case. At least delta is universal. What's important is you can always color simple graph by edges of the simple graph with the delta plus 1 colors. So this is surprising theorem. So Beijing's theorem is false in general for general graphs. So for instance, if I have a 3-vertex graph with parallel edges, so if this is G, then maximum degree is 4, but the edge chromatic number is what? If you look at these 6 edges, all these 6 edges are pairwise adjacent. So it's 6. In general, there's something called the Shannon's theorem, which we are not going to prove, that the edge chromatic number is like 2/3 if you have a parallel edges. So 2 delta, you can improve it. Okay, I guess yes. Any questions? All right. Yes. So with Beijing's theorem, there's a I mean, the proof is a bit complicated, but once you have a correct inductive claim, so there's a nice induction claim that is a lot stronger than Beijing's theorem itself, and that gives you a very nice easy proof. Okay, I think you might have to have this, but I don't remember exactly. All right, so maybe some question mark. All right, so what we're gonna do is to state this lemma. Okay, so let G be a simple graph such that maximum degree of G is at most K, and that free via vertex. And here I have a list of edges, so E1, E2 up to ER be some edges incident with V. Now suppose that G minus E1 minus E2 minus ER has a K edge coloring such that now E1 has at least at least one color missing at both ends. So meaning that when in this K edge coloring, out of these K colors, at least one color doesn't appear at any of the other edges incident with one of these ends, right? So you have E1, E2, ER. So when you look at this edge, there are edges here and other edges here, right? And all these edges doesn't use at least one color, so I can change the color of E1. No, not quite. I'm not changing. E1 is not yet colored. E1 doesn't have any colors, but at least one color choice is available. And each of E2, E3, EK has at least two colors missing at both ends. Okay, So for E2, you not only have one choice, but you have actually two choices to extend. For E3, you have two choices. Then the claim is that edge chromatic number is at most k. So you can actually extend all the coloring. Right? So in other words, in the figure, so I have a color like this, red, blue, and blue, red. And do I have any other color? Green, green, green. Quickly running out of the colors. Blue, etc. Now, if I have four colors, then maybe yellow doesn't appear on both ends of E1, right? Both ends of E1, there's no yellow, so perhaps I can extend this yellow over here. Okay, maybe I really need a yellow color somewhere. Okay, yellow. Oh, okay, I cannot see that. That's not black. Okay, black. So for this edge, I cannot have a black, I cannot have a blue, I cannot have a red, I cannot have a green. So it doesn't have many choices. So that's not what we want. Maybe if I delete green, then now it has green as one of the choices. But I cannot have a two. So I need many more colors. Okay. So anyway, that's what we want, right? So each edges have at least one color choices, and except E1, everything has at least two choices for colors. But unfortunately, some of these choices are equal. So that's why we cannot extend it immediately. I forgot to tell you why this lemma implies Wiesen's theorem. To see why this implies Wiesen's theorem, you just take a k to be delta plus 1. If you take a k to be delta plus 1, then let's imagine that you apply induction. So when you do is what you apply induction on G minus all edges incident with V. So it's same, yeah, okay, let's say all edges incident with V. And this one has as chromatic number at most, by induction, it's at most k, right? And when you look at the edge EI, since none of the edges incident with V are colored, and this you have a delta minus 1 colors of used at this vertex, is k minus 1. Oh, actually k minus 2. So delta minus 1 is k minus 2, right? So that means for each edge EI, you have two colors available. And this lemma requires at least two colors for almost all edges except one edge, which only requires one color available. And we're satisfying all of these conditions, right? We have more than that. Every edge has two colors missing at both ends. So that's why by applying this lemma, we deduce that edge chromatic number of whole graph is at most k. So Wiesen's theorem is just consequence of this lemma when k is equal to delta plus 1. Okay? So how do you see the proof? So we apply induction on R. So if R is 1, if you have only one edge, then you have to fill in. Then it's trivial. Because you have one color missing at both ends, so you color E1 by that color, and that's k edge coloring of the whole graph. Right. So I can assume, so we may assume R is at least 1, and bigger than 1. So let C be such a k coloring, k edge coloring. G. Now let F1, F2, F3, Fk be the set of colors such that if color if X is in Fi, that means the color X does not appear at both ends of EI. Right. So I didn't take all the colors, I just take the some colors, right? For E1 I can choose one color, for E2 I can choose two colors, for E3 I can choose two colors, etc. So I can do that. Right. So if a color alpha does not appear, okay, no. If color F is in exactly one of F1, F2, Fk, then, okay, let's say Fi, then we color EI by alpha, right? So if you have an edge where one of them is alpha, and this alpha never appears in any of these choices available colors, then we color EI by alpha. And then we apply induction with the remaining edges. Because even if I color this EI by alpha didn't appear in any of the set Fi, so those things are still same, right? So instead of E1 up to ER, now we have EI minus 1 and EI plus 1 up to EK. So you have one less, ER. You have one less edges, and all the conditions are satisfied. Every edge has exactly at least one available colors at both ends, and except E1, or except one edge, you have at least two colors available. And I could be equal to 1. In that case, every edge has at least two available colors, so that's good enough, right? So this implies that G, the edge chromatic number, is at most K. Therefore, we may assume that if alpha appears in any of this set, then alpha appears at least twice. Right. What does that mean? That means the following. Just look at this thing. This has size 2r minus 1. So since the number of entries in this F1, F2, Fr is exactly 2r minus 1, and each number appears at least twice, the number of colors appearing in the union is at most, less than r, right? Because if you have r distinct colors, each of them appears twice, then you need to have 2r, but the size is 2r minus 1, so it's less than r. And r is less than maximum degree, and the maximum degree is less than k, right? So there is a color, right? There is a color alpha not in any of these sets. Right? There is one of the colors which doesn't appear in any of these sets. And not only that, oh, I should have said a little bit more. Okay, so that means number of colors appearing at V in G delete E1 ER plus number of colors appearing in F1 union FR. When you add them together, this is less than the degree of the vertex V, which is less than or equal to delta, which is less than or equal to K. So there is a color alpha not appearing at V in G delete E1 delete ER and not in F1 union F2 union FR. Right, so some color never appear. Yes. So here's E1, E2, E3, ER. So let's say this is V1, V2, V3, VR. This is V. So color alpha never appears in any of these dots. So this is a list of choices. And let's say beta be the color in F1. So there's a unique color. Okay. Now let's look at the subgraph induced by alpha and beta. Right. So let H be the subgraph of G consisting of E1 and all edges of color alpha or beta. By the way, I should say maybe we color E1 by beta first. So here we're gonna use this color to color this. So this is beta. And then I take a subgraph H consisting of all edges of color alpha and beta and pick a component. Okay, let's say let C be a component of H containing E1 because it's colored by beta, so there will be a component. Now we have to look at this property. The maximum degree of C is at most 2 because you only choose edges of color alpha and beta. So in each vertex you can have maybe one edge of color alpha, one edge of color beta, and that's it. So maximum degree is 2. So C is in connected graph. C is either a path or a cycle. But degree V has no edges of color alpha, so that means C is a path ending at 3, or you can say starting at 3. So there is a path. So let W be the other end of C. So this path actually goes somewhere, and let's say W. Now what we do is we swap alpha and beta in edges of C. Right? So we change our beta to be alpha and alpha to be beta. What's going to happen? For all vertices, except V and W, the set of colors used there is not changed, right? So if it's an internal vertex of C, then we used to have alpha and beta, and then it becomes beta and alpha, right? Nothing changes. The only place there might be any change of the list of colors used at the edges incident with that vertex is the ends of this path, V and W. So this could be one place where the set of available colors change. So what used to be beta become alpha. And this is the vertex where it could be like, I mean, we don't know the color of this edge. But what we care for the induction is whether or not these edges are safe, right? So, but W could be incident with at most one of E2, E3, ER. So that may destroy one element in Fi, right? Because maybe by swapping this color, you certainly have beta, and maybe Fi had the beta initially. Then you have to destroy beta. Beta is no longer available because it's used in one of the edges instead with the Vi. But still you have one color available for Fi, and all other edges still has two colors available. Now, right? So that yeah. So is that clear? So if W is incident with EI, then let E1 prime to be EI and E2 be E2 prime, E3 prime, ER minus 1 prime be the other edges. Edges other than. Okay. What would be the easiest way to say? Okay. Maybe I say this. E1, E2, ER minus E1, EI. Okay. Then we apply. If W is not incident with any EI, then it doesn't matter which one I take. So let's say E2 prime is E1, no, E1 prime is E2, and E2 prime EI prime is equal to EI plus 1 for all I. I could say that. Then we apply induction. To G, delete E2, delete E3, delete ER to obtain the number of G's and most K. Right. So that's the proof. So this is again kind of campy chain argument. So we pick a component consisting of edges of color alpha or beta, and then we swap all of edges, we change alpha and beta in this component. And for edge coloring, there's a nice property that this will not ruin a lot, right? I mean, for most vertices in the middle, you still have the same set of edge colors available, and at the ends you have this different situation happening, but there are only two vertices that are concerning. So that's Fielding's theorem. Okay. Now we move on to the list coloring. So as we saw in the proof of Fielding's theorem, sometimes it's better to have a stronger induction hypothesis to prove something. And list coloring is an attempt to do that too. So instead of giving the same set of colors available for every vertex, we're gonna give a list of colors available separately for every vertex. So let G be a vertex, graph, and a list assignment L is a map that maps each vertex to a set LV, so each vertex V to set LV of colors. Okay, so that's a list assignment, and an L list coloring of G is a function C from on the vertex at G such that CV is always in LV, so each vertex is colored by one of the colors in the list, and whenever two vertices are adjacent, then you have to have distinct colors. Right, so that's a list coloring, and then we say G is K choosable or K least colorable if whenever the LV is equal to K for all V in V of G, G has an L list coloring. Yeah, so for all possible, yeah, so in other words, okay, maybe I should say list assignment. For all list assignments L, whenever this is the case, then have an L list coloring. So then list chromatic number or choice number. Sometimes this is choice number. Yeah, it has two names used commonly. Is the minimum K such that G is K choosable. Okay, so that's the definition of the list coloring. So for instance, list chromatic number. So this is easy to see that this number is upper bound for the chromatic number because, well, whenever I have a graph, I give the same list to every vertex. And that doesn't change, and then if this is k list callable, k choosable, then in this situation I can always find the coloring satisfying this list, so that will give me a proper k coloring. So this is trivial, but then in general the gap could be arbitrarily big. So here's an example, K33 complete bipartite graphs, and here's I give list like 1 2 2 3 1 3, and same here 1 2 2 3 1 3. And if I choose by symmetry let's color by 1, then I cannot use color 1 here, and then I have to choose 2 and 3, and then I cannot choose any of them. So that means least chromatic number of K33 is not 2, it's bigger than 2. All right. But still, it's easy to see that the least chromatic number of graph G is the most delta plus 1. And the proof is same. Why? Because if I have a vertex of degree delta, then apply induction in the remaining, right? So induction, it's same proof, induction on number of vertices, and let L be a list assignment, so that size of L is at least delta plus 1, delta G plus 1. Okay, now apply the induction to G delete V to obtain a L list coloring of G delete V. And once we have it, the set of colors appearing in the neighborhood of this vertex is less and most delta and most maximum degree. So there must be a color not used in the list, right? So every has some color not used in the neighbors of V. So we color V by that color. So it's only a proof of sketch of the proof. So many of the proofs on vertex coloring can be actually translated into a proof on list coloring. Okay. So the motivation to study the least chromatic number is because in some cases you can actually prove very nice theorems inductively by using this stronger assumption, and that's what's known. So this is like, remember, every planar graph is bicolorable by easy proof. You originated from Hewitt or Kempe. Now we're going to prove that every simple graph, planar graph, is 5 choosable. That's surprising. So in other words, least chromatic number of planar graph is at most 5. And this is theorem due to Thomason in 1994. Okay, so Carsten Thomason was visiting KAIST a few years ago. He's a professor at DTU, Technical University of Denmark, and our math department has a dual degree program with DTU. So one of my master students actually had a joint degree at DTU, advised by Carsten Thomason a long time ago. All right, so the proof is quite nice. So we again make a stronger statement. So the claim, so let G be a simple plane graph such that every inner face is a triangle and the outer face is bounded by a cycle C, let's say V0, V1, V2, V3, these are vertices of this cycle. Let L be a list assignment of G so that L V1 has one color. Okay, I mean, if you have one color, why not just say 1? LV1 is 1, LV2 is 2, so these two vertices of color 1, 2 fixed. And LVI has size at least 3 for all I bigger than or equal to 3 and K and LV. All other vertices have the, at least 5 available colors. For all V not in, then G has a L list coloring. Okay, so the claim is definitely stronger because vertices on the infinite face doesn't have 5 choices, only has 3 choices available. Vertices inside have 5 choices, but vertices on the boundary only have 3 choices available, and yet the Thomason's proof shows that this will make the proof actually easier, not harder. And this also, and it's easy to see that this implies the theorem that every planar graph is 5 least colorable, because I can just ignore unnecessary colors, and right, if every vertex has 5 colors available, then it satisfies the assumption here. All right, so why is this the case? And the proof is by induction. Oh, by the way, I forgot to tell you that what another reason why this implies the theorem, because when you have a planar graph, you can always find the bigger planar graph by keep adding edges and edges and edges, so that every inner face is a triangle. And you can even continue further so that infinite face is also triangle, right? So every graph, every plane graph is a subgraph of a triangulation. So that's one of the reasons why this claim is enough. Okay, so we do induction. So if the cycle C has a chord, so that's we are considering, we have 2 cases. If C has a chord, let's say Vi, Vj. If there's an edge connecting Vi and Vj, let's say V1, V2 are here. What we do is we apply induction over here first. Right? So let's say this is G1, G2. We apply induction to G1 first to get a L list coloring C1. Now C1 determines the color Vi and Vj, but these 2 colors are distinct, right, because they are adjacent. So now after that we apply induction over here, and this is definitely smaller than our original graph, and this is definitely smaller than original graph, so I can apply induction hypothesis. So I have these 2 pretty colors, so I can extend it. to G2, we have a L list coloring of G. So that's easy case. So we may assume G has no chord, right? So now here's a V1, V2. Now let me look at the neighbors of V1. And because every interface is triangle, it looks like the path. Right? Now, let's say this is VK, and VK has 3 available colors. All right. Out of these 3 available colors, 2 of them will be the different colors. So let alpha, beta be the colors in VK, so that alpha, beta are not in V1. Okay, so here you have 2 available colors, alpha, beta, and let L prime of W be L prime minus alpha, beta if W is a neighbor of V and W is not equal to VK and V1. Okay, so these guys have used to have 5 colors available. Now I'm creating a new list by deleting 2, potentially 2, maybe delete less. I'm deleting alpha and beta in each of them. And that L prime for any other vertex is same as W. If W is VK or W is V1 or W is non-adjacent to V1. Okay. Now G delete V1 has a L list coloring. Why? This is by induction hypothesis. When I delete V1, remaining is still plane graph where all interfaces are triangle. The infinite face is bounded by 3, and yes, right. So why not? Oh, am I cheating here? Oh, I'm cheating here a lot. Okay, let's fix it. I realize where it's gone wrong. Okay, so let me fix it. That was too quick. So this is okay. This is not V1, V2. This has to be VK, V1, and here's a V2. Okay, so alpha, beta are the edges. It's wrong. So here's alpha, beta. So alpha, beta are still colors. Yes. So this was why it was confusing. So yeah, it's the same. So this W is not V1, not a neighbor of VK, and it's not VK minus 1 or V1. Right. Now we apply induction over G delete VK. Right. So we apply induction over here. Now these 2 vertices are already pre-colored, and everybody here has 3 choices. Everybody here has 3. Everybody here has 3 choices. So we apply induction over here. So we have a coloring. Let's say this coloring is C. Then all neighbors of VK all neighbors of vk other than vk minus 1 as have neither alpha nor beta, because I have removed alpha and beta, and I chose alpha and beta so that they are not in the list of v1, so v1 has different color. But the only worry is what if cvk minus 1. I mean, that's possible situation, right? So vk minus 1 may have a color from alpha or beta. So we color vk minus 1, no, vk by alpha or beta, just to ensure that color vk minus 1 is different from color vk. Since we have two choices, one of the choices will work. So that's the proof. Very nice, easy proof. Okay. So this is the theorem. So every planar graph, every loopless planar graph is 5 colorable, 5 choosable. So this is another proof. All right. So you may hope that maybe or simple planar graphs, if all simple planar graphs are 4 choosable, then we have a proof of 4-color theorem. But that's not the case. So not all planar graphs are 4 choosable. So that's unfortunate, right? Because people wanted to invent this notion in order to prove the 4-color theorem. And it turns out that there is an example. So in 1993, Voigt found an example of planar graph with 238 vertices, and then later Gutner reduced it to an example. It is actually surprising. 3 colorable plane graph on 75 vertices, not 4 choosable. And later, Miriam Rizkani in 1996 had a paper showing that there's a planar graph with 63 vertices which is not 4 choosable. And when she was writing this paper, she was an undergraduate student in Iran. And you may know her name because she won the first Fields Medal for a woman. So she won the Fields Medal in 2014 in Seoul. Okay, so the hope of proving that every planar graph is 4 choosable doesn't work because there's these examples. And so far, this is the smallest possible graphs. I mean, no one knows whether there's a smaller example. This is the smallest known example, which are not 4 choosable and planar. There's a very nice theorem by Alon and Tarsi, and they showed in 1992 that if graph is bipartite and planar, let's say simple, then the least chromatic number cannot be too big. It's at most 3. So as long as graph is 3, I mean, here we have an example where graph is 3 colorable but not 4 choosable, right? So chromatic number is 3 and least chromatic number is 5. There is a gap. Can you have a bigger gap? Can you have a chromatic number 2 and the least chromatic number 5? No, the Alon-Tarsi's theorem says that if chromatic number is 2, least chromatic number is 3, at most 3, if graph is bipartite. Okay, so that's it for today. All right, so we're gonna continue with some list coloring problem for edge chromatic number, and then with other topics on coloring.